Okay, so now I just wanted to just spend a few minutes just reviewing for the first test right here. And remember, I'm just going to go back and say, remember we defined work right here. Work is defined as the force times the distance. So we had to push something and move something, force times distance. And we said when we do work on an object, we're transferring energy right here. If I lifted the book up onto the table, remember, I was doing work on the book gained energy, I lost energy right here. Remember, the units of work are in joules right here. So lifting up an object, you're doing work, you're going into lifting it up, you're losing it, and it's going into potential energy right here. Potential is mgh, where h is the height right here. Remember, that's the weight of it. So it's just the force, which is the weight times the height right there. Now, if it fell, then the potential, it's losing it right here. Well, if you put your work into speeding up something instead, well, moving energy is called kinetic energy. Kinetic energy, remember, was 1/2 mv squared. Remember, it goes as the square. It's not v, it's v squared. So if you double the speed, you have 4 times the kinetic energy. Doubling the height, you only have twice the potential energy. So don't get those mixed up right here. So now when something falls, it's losing potential, it's gaining speed, so it's gaining kinetic, and so the potential is just being shifted over to the kinetic energy. When it's moving upward, it's slowing down, so the kinetic energy is being shifted back to the potential. So if we have a pendulum swinging back and forth, it's just going from kinetic to potential. Kinetic at the bottom, potential at the top, right here. Now, if this object is moving, you're in your car and you slam on your brakes, that means all of your kinetic energy is going into here. It's going into a force times a distance. It's the brakes times the distance it took to stop, and that would really go into heat because your brakes would get hot right here. So what's happening is things are just moving around right here, and what they say is energy is conserved. It means you can't create or destroy energy. It just shuffles around, makes it nice for physicists because they can just keep track of where all the energy is. It can't be destroyed right here. So even throwing a projectile, throwing a rock in the air, it's just going from, you had to apply a force and distance as it was in your hand. As soon as it left your hand, it had a lot of kinetic energy. Flying through the air, lifting up, it slows down, goes into potential, comes back down into kinetic, hits the ground, goes back to a force on the ground times a distance. You're bumping something. Okay, so, and we said if you're spinning, then you also have even more kinetic energy. You have kinetic energy due to spinning right here, which we said was the equation is the same, except instead of m, it's rotational mass. And instead of speed, it's rotational speed. Remember, rotational mass, that depended on how far out the mass was from the center of the axis of rotation. So we said a hoop had the largest rotational mass, and the disk had the medium amount of rotational mass, and the solid sphere had the least right there. Okay, so there is energy conservation right here. Then we had Newton's laws. His second law was what? The net force equaled ma right here. So if I ever ask on the test what the net force is, just look and see what the a is right here. If it's not accelerating, then the net force must be 0 right here. And then we also had Newton's third law. For every action, there's an equal and opposite reaction right here. So these two are always on different objects right there. Okay, and now, if from these two statements right here, from these two statements, Newton introduced a concept called momentum, which is mass times velocity. And because of these two statements right here, this mass times velocity is also conserved. That is, you cannot create momentum, you cannot destroy momentum. All you can do is transfer it to something else. Whenever you put the brakes on your car loses momentum, but the earth picked it up right here. So this is a conserved quantity right here. We also had rotational momentum. That's also conserved, which is the rotational mass times the rotational speed. So when an ice skater pulls in her hands and she's spinning, she's making her rotational mass smaller. Her rotational speed grows right here. But the product of these two, rotational momentum, is the same right here. Okay, so there is momentum. Again, it just comes from Newton's laws right here. Now, if we have an object just falling right here, we know, at least when we're near the surface of the Earth, the only force we have is the weight, which is just mg. We don't have to use the big G, the m over r squared, because we're near the Earth's surface, where g was 10 meters per second squared right here. Now, if something is falling, we said that the speed increases by 10 meters per second for each second. That's what the acceleration says. It tells you how much the speed changes every second. So if I threw it at 30 meters per second, 1 second later it'd be 40, 2 seconds later it'd be 50, 3 seconds later it'd be 60 and 70 and 80, right there. If I was throwing it upward at 30 meters per second, then it would slow down 10 meters per second. So if ascending, the speed decreases 10 meters per second every second, right here. And at the top of its path, A is still G. A is still, it's always downward. What goes to zero at the top is the speed, right here. Now, if I wanted to find the distance that this object moves in those 2 seconds, just from that to that, you always just take the average speed, the average between your two times, the average between 30 and 50 is the one in the middle, which is 40, times the time. Well, that was 2 seconds. So it'd be 40 times 2, which is 80 meters. So if you threw an object down at 30 meters per second, in 2 seconds, it would be going at 50 meters per second, and it would be 80 meters below you, right here. So get that down for the test right here. Remember, we also had a definition of acceleration. It was the change in the velocity over the time. And remember, velocity is both speed and direction. So if either one of these change, you're accelerating. So you can either speed up, slow down, or turn. In all those cases, you're accelerating right here. When we're turning, let's say we're going in a circle right here, circular motion. Your acceleration is always toward the center of the circle, and the strength of that acceleration is v squared over r right here. So if you don't have that, if you're not accelerating that great, then you're going to probably spiral out. If you accelerated more than that inward, you'd probably spiral inward right there. But the direction of the acceleration is also inward. And since F equals ma, the direction of the force would also be inward as you're going around right here. Over here, if your acceleration is in the same direction as your velocity, then you're speeding up. If your acceleration is in the opposite direction you're moving, then you're going to slow down. That's why when you throw something up, G is always down. If you throw something up, you're slowing down. On the way down, your acceleration's down and your velocity's down. That's why you speed up on the way back down. So this, hopefully, will help you with that test. Again, it's being handed out on allowing you to look at it on Monday, but again, once you open it up and look at it, you only have 2 hours to take the test, and you have a whole week to think about it, so wait till you're prepared to take the test before you start it right here, because then you only got 2 hours. Okay, and again, look at that, the test bank under the announcements in Canvas. Go to that website and you can look at the test bank and do questions there. That'll help you with the test right there. Okay.